Welcome to today's Explainer, where we are decoding the profound architectural differences in how AWS and Google Cloud Platform handle internet routing. Look, if you've spent any time designing cloud networks, you already know that ingress and egress traffic flows are literally the lifeblood of your architecture. But what happens when the fundamental assumptions you've built your entire career on in one cloud just don't map to another? Well, today, we're stripping away the marketing jargon, we're looking strictly at the routing tables, packet translation, and control plane architectures to truly understand this massive paradigm shift.
So, let's jump right in with a question that honestly trips up a lot of veteran cloud architects transitioning between platforms. Does Google Cloud actually have a physical internet gateway? In the AWS world, the internet gateway is a tangible, provisioned resource. You can easily point to it. But when you switch gears to GCP, the answer gets a whole lot more nuanced, and understanding exactly why that is absolutely crucial for unlocking highly scalable network designs.
Here is our roadmap for this explainer. First, the core gateway difference. Second, the AWS routing baseline. Third, GCP's software-defined approach. Fourth, private egress and cloud NAT. And finally, an architectural comparison summary.
Section 1. The core gateway difference.
Okay, the conceptual shift here is absolutely massive. We're talking about moving from AWS's component-based infrastructure directly into GCP's fundamentally software-defined networking model. In AWS, you're basically acting like a traditional physical network engineer. You build a network by creating discrete, isolated objects and literally plugging them into each other. It's incredibly component-driven. GCP, on the other hand, it operates on a ubiquitous, global software-defined network, or SDN. Rather than explicitly attaching physical or virtual objects to enable routing, you are configuring logical policies on a fabric that is already everywhere. This single core difference dictates absolutely everything about how your packets eventually reach the public internet.
Moving to Section 2, the AWS routing baseline.
Let's establish our baseline. In AWS, getting bidirectional internet access is a very literal, step-by-step traffic path. If you want a compute instance to talk to the internet, you first put it in a subnet. Then, you configure that subnet's route table so the default quad 0 route points directly to an explicitly provisioned internet gateway component, your classic IGW-XXX resource. Finally, you make sure the instance has a public or elastic IP mapped to it. The internet gateway here is a distinct entity. You have to create it, manage it, and attach it to your VPC. Without that discrete object plugged in, your traffic goes absolutely nowhere. It is a very deliberate, object-oriented approach to networking.
Section 3. GCP's software-defined approach.
Now, if you look at a GCP route table, you are indeed going to see a default route for quad 0, and its next hop is set to something called the default internet gateway. But here is where the paradigm completely breaks. You are actually looking at Andromeda. Andromeda is GCP's underlying planetary scale SDN. That default internet gateway you're seeing, it's essentially a ghost. It's purely a logical abstraction provided by Andromeda. You don't create it, you don't attach it, and most importantly, you don't manage its capacity. It is simply an inherent property of the network fabric itself.
So, you might be wondering, how does the actual packet translation happen without a physical appliance? Well, by simply assigning an external IP address to a compute engine instance, GCP automatically enables one-to-one network address translation directly at the physical host layer. The hypervisor running your virtual machine handles the packet translation right then and there. This completely bypasses the need to go in and modify subnet route tables to point to an external gateway object, because the translation happens before the packet even leaves the physical host. It is incredibly efficient.
And this brilliantly illustrates why subnets in GCP are inherently capable of internet routing without ever needing to be explicitly labeled as public or private at the configuration level. Think about it. In AWS, a subnet is public only because you actively wired its route table to that attached IGW component. In GCP, because the internet gateway is a logical abstraction that's globally available on the SDN, and translation happens right at the host level, every single subnet natively has a path out. Whether a specific instance actually communicates with the outside world just depends on whether you've assigned it an external IP and allowed it through your firewall rules. It's a massive shift in how you plan your IP spaces and define your security perimeters.
Section 4. Private egress and cloud NAT.
Let's apply this paradigm shift to a scenario we all deal with: outbound-only traffic. What if you have resources that absolutely should not have public IPs, but they still need to securely download OS patches or hit external APIs? For these private resources, AWS forces you to route traffic through a provisioned zonal NAT gateway appliance.
And if you've ever dealt with bandwidth bottlenecks or the eye-watering costs of pushing petabytes through a single AWS NAT gateway, you know exactly the pain I'm talking about here. GCP, however, utilizes a fundamentally different mechanism. They layer a regional cloud NAT directly onto their distributed SDN for this egress-only traffic.
Notice how the architecture splits here. In GCP, the cloud NAT is configured on a cloud router. But here is the absolutely critical distinction. That cloud router acts strictly as the control plane. It handles the BGP sessions, it manages the config, and it allocates the NAT IPs, but it never actually touches your traffic. The distributed SDN, Andromeda, handles the data plane. It performs the Source NAT translation transparently across the entire network fabric. Because there's no single virtual appliance sitting in the data path choking on bandwidth limits, your outbound traffic simply scales with the underlying fabric. It's an incredibly elegant solution to a notoriously expensive cloud bottleneck.
Section 5. Architectural Comparison Summary.
Let's bring all of these nuances together into a clear side-by-side view. Look at how moving to logical SDN abstractions radically transforms your network. Under component isolation, we're shifting from creating explicit, rigid AWS gateways to relying on Andromeda's fluid, logical abstractions. For scope, AWS restricts you with VPC-wide attachment limits, whereas GCP inherently routes globally across regions. Subnet typing changes drastically too. AWS requires explicit routing table definitions to make a subnet public, while GCP subnets are just inherently capable right out of the box. And perhaps most importantly for high-throughput applications, data plane bottlenecks are entirely avoided in GCP because its distributed SDN performs packet translation without introducing those physical appliance choke points. Take a second to let that structural difference really sink in.
Grasping these foundational differences, that is exactly what elevates a good network architect to a great one. It's about knowing not just what buttons to click in the console, but how the underlying packets are actually flowing across the silicon. So I'll leave you with this. Once you fully grasp the power of Andromeda's SDN abstraction and the total elimination of middle proxy bottlenecks, how will it change the way you design your next resilient cloud network? Think about the possibilities for scale, cost savings, and raw operational simplicity. Thanks for joining me for this explainer, and keep building smarter.